Hi, my name's Dan, and this video is one in a short series of videos that I'm doing on digital circuits to do adding of binary numbers. And in this one, we're going to do a 4-bit binary adder. It's part of a larger suite of videos which go from the fundamentals of logic gates all the way through to building a fairly simple CPU that will actually work and will be programmable. So there's a in the description below, there's a roadmap of where we're going with that. This video relies on knowledge from previous videos, so I guess you can watch it in isolation, but don't blame me if you don't understand everything if you haven't watched my other videos. Of course, there are lots of other videos out there, and you may have prior understanding, so that's all fine. Also, in the description down below, there is a link to this software which I'm using, which is Digital Works. It's free digital electronics simulation software. Excuse me. Right. So let's plow in. We want a 4-bit uh, binary adder. And the reason for 4-bit is because the overall aim for this big suite of videos is that we're going to create a 4-bit CPU. So pretty much everything that we do in this sets of videos will expand up to 4-bit. So if you've been watching the previous videos, you'll see that we've created a half adder and a full adder, which I've called the 1-bit adder. And one of these adders does 1 bit in your binary, binary numbers, and so fairly obviously for a 4-bit adder, you need 4 of these 1-bit things. I encourage you, if you're following through these videos, to actually go through the whole of this creation process yourself. Because it's actually quite satisfying to end up with with these circuits in the end. So I've thrown those 4 in. I'm just going to put some tags in. So these tags will allow us to turn this circuit into a macro. So I'm going to talk about the tags that I'm putting in. So those 4 that I created down here are going to be the output. I'm going to do A and B inputs, both of which are 4-bit binary numbers as well. So 1, 2, 3, 4. And it's going to be, I will annotate these so that we know what we're doing with the different bits, parts of this. And we're going to need a C in for the whole circuit and a C out. Here we go. So I will do some rearrangement of this, I think. So one thing you may be thinking is if we've got 4 of these full adders, why do we actually need a full adder for the least significant bit, which is going to be this one here? And the answer is that I've positioned this the wrong end. The answer is because there are some arithmetic tricks that you can do if you use a full adder for your first digit as well, which allows you to effectively push an extra digit into the mix. I'm not going to dwell on that in this video. In the next video, when I'm going to show subtraction, I will use that. So this is a case of trust me, but you will see it in the future. So I'm going to call this A 3 to 0. And let's make that bigger actually. I'll make it a 10-point annotation. And this is going to be our B input. B 3 to 0. This is going to be our output. Out 3 0. This is going to be our overall carry in. C in. And finally our overall carry out. See out. So the next bit is wiring up the individual bits. Let's have the sums first. The output. I'm not going to spend ages trying to make this perfectly aligned. Just enough to see what's going on. Then inputs. So this is um, our half adders are going in the order of most significant bit down to least significant bit. So this is column 3, column 2, column 1, column 0. And we've lined that up with the outputs down here, and we're going to do it with the inputs. So the A inputs, 3 to 0, need to go into the individual half adders like so. Yeah, I didn't give myself a lot of room there for that, did I? I don't care if it's a little bit scratty. It's going to be quite a lot of scratty. If I was doing this for commercial purposes, I would make this neater. And then similarly, so for the B inputs, they need to go to the individual B inputs of these half adders. Right. So C in is going to be fed into digit 0 here, the 1-bit adder. And what we need to do in order for this carrying process to work is we need to go from C out from each one to C in of the next column up. And so this is the way that they're chained together. And then finally, the highest digit C out, we're gonna turn that into an output, which is basically in case our binary number overflows, it goes beyond 1111, which is 15. Now that could be a lot neater. So maybe when you're doing this, you might want to neaten this up. That's up to yourself. So the next process, go to the template editor. I tend to be more worried about making sure the template looks and is logically neat than I am sometimes with the underlying circuits. It would be easier to see what's going on in the underlying circuit if I was quite a lot neater than this. I didn't really plan what I was doing ahead of time very carefully. So I'm going to expand this out so that we can have a bit of space for our inputs. And I will probably compress it back down again when I've worked out exactly how much I need. So this is going to be our A input. I'm just using Control C with a group there, then Control V to paste it. So let's have another group, which is not going to be our B input. We've already got one of those labeled C in, so let's keep that. I'll get rid of that annotation and call this too far. A 3 to 0. And similarly B 3 to 0. B 3 to 0. I'm going to move the C in a bit closer because I'm going to shrink this down to about there. I haven't changed the overall name, so this is a 4-bit header. Let's kind of center that. Our sum needs to be 4 digits instead of 1 digit, so I'm going to select those, copy and paste. Get rid of the single pin there. Change this annotation to sum 3 to 0. So the 3 to 0 indicates that there are 4 bits and we're going from most significant down to least significant, which is the conventional way of representing binary numbers from left to right. Have we got everything we need? A, 3 to 0, B, 3 to 0, C in, sum 3 to 0, and C out. So I've changed the name to a 4-bit adder, and I'm just checking the main circuit that this is everything that I'm going to need. And I believe it is. So I'm going to do the wiring up that I need to do. Because this is going to take a couple of minutes, I'm going to speed up the video and you can listen to some music while you watch. However, if you're doing this process yourself, you might want to pause the video, listen to the music later. Right, there we should be all right, all wired up now. So we're going to save this as our 4-bit adder. Save as. We're in the macros. Click on adder 4-bit. The reason why I put the word adder in the front is so that these parts arrange themselves according to type alphabetically, makes them easy to use. And so the next thing that we're going to do, as always, is we're going to make a circuit to test our macro. So 4-bit adder. And I'm going to need 8 inputs. We've got an A input and a B input. We're going to need another input, which is the C input. I'm going to need some 4 outputs and our C out output. And once again, this is kind of fairly straightforward stuff. So I'm going to fast forward the video again as I do this process. Right, that's me all wired up and ready to test. So one thing I'm going to say is that, in fact, I'm not going to do an exhaustive test. I'm not going to check every 4-bit binary number added to every other 4-bit binary number, then with C in or not C in to see what the output is, because that would take quite a long time. So I want to use some kind of representative tests. And we're already up and running, which means that certainly our first test has worked, where if A is 0, 0, 0, 0, and B is 0, 0, 0, 0, C in is also 0, then our output is 0, 0, 0, 0, and our C out is 0. Let's add 1 and 3. 1 and 3 gives us 4 on the output, if you know your binary numbers. Let's add 10 and 3. Which should give us 13. What's 13 as binary output? We've got 8 there. That's the 8's column, that's the 4's column, that's the 1 column. So that is 13. Let's add 10 and 10. This should give us 4 with a overflow. So let's see if that's right. So the highest number we can get is 15. So when we go back to 0, that's 16 with the overflow. In fact, the C out is effectively the next significant bit. We could conceptually have that over there. So if that's the C out, means we've gone 16 or above. So it's 16 plus the 4, which is 20, which is what we've put in. Let's add in the C in, and that should go up to 21. And it has. Okay. Let's put this down to zeros. And there, but let's have 1, 1, 1, 1. And this gives us an instant overflow into 0, 0, and then but the C out is 1. So it seems to be working. and I'm happy enough with that to leave this here. So that's a 4-bit binary adder. If you wanted to make more bits, like an 8-bit adder, the process is obvious that it's just chaining more of these 1-bit adders together to create that circuit. Um, so we're nearly done with simple addition, except in the next video I'm going to show you how to do subtraction. But that's it from me for now.